unfortunately there is a time delay, so let me just have time to so please check my recorded lecture after this session is over. And I'm not quite sure about the recording volume, so I just set it to just the middle one, so not very low, not very high. So first of all, let's try to just make a recording today, and when you give me a feedback about the quality of our recorded lecture, then I will try to improve it. So there are two systems separately installed. So this system is from our college and university, and this is my own. So they are not connected. So please understand this situation. And I wanted to first check your attendance again. So can you hear me clearly? Okay. Okay. And 이재혁 씨, 고하늘 씨,
네.
신준호 씨,
네.
이승빈 씨,
네.
이정태 씨, 이충화 씨, 네. 정상아 씨, 홍주표 씨, 김민선 씨, 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨, 조대현 씨, 네. 최순주 씨는 또 김성수 씨, 미스터 마니페. Good morning, everyone. Anyway, I think that it's good to make a recording. So instead of just our lecture unrecorded, but maybe that will be very helpful for your review of our lecture. So that's the reason I spend some time to some minutes to install this system, and we are already lecture 11. And how about your homework number 10? So you had, I remember, if I remember correctly, you had 3 problems. Was it okay? So any problem? No? So the first problem, P1, was related with our previous homework problem. So at the time we have assumed that WP, the depletion width related with the p-type region was about 100 nanometer. That was our previous problem. So the one in lecture 9. However, in lecture 10, we used more realistic value. Oh, the range is more or less same, but for this system, this means that so 10 to the 20 and 10 to the 17. For this system at 300 Kelvin, at equilibrium, we have about 120 nanometer for our depletion width. Of course, we have to consider also N-side component. So, however, it is just given by 1,000 times smaller than Wn. So, when we consider just sum of them, so maybe that can be regarded as the total length of depletion width. However, that will be almost entirely the same with our p-type region depletion. Depletion width, usually we call it as a width, not length. And how can I say, it is only because this dominant of a p-type width is given by the property of our junction polarity. We have high n-type region and relatively low or moderate p-type region. So that's the reason why we have p-type region dominant. And if we consider, for example, the deep opposite way, p plus n junction, where we have really strong p-type region, then you can say that the total depletion width will be determined by W sub n. So only we will have only meaningful value for our say n-time region. So relatively lowly doped region only have the depletion region. So maybe you can remember this one. So I hope that you can easily solve P1 because it is just a repetition of our previous lecture. And if we go to the P2 and P3, instead of just solving the equilibrium case corresponding to 120 nanometer depletion width, I ask you if we apply forward bias 0.1 volt or if we apply reverse bias negative 0.1 volt to our system, then what will happen to our system? That was our problem 2 and 3. In this case, maybe you find that WP and of course WN, both of them are slightly reduced, and in this case, we will find that the depletion is will be slightly increased. But you can also find that the difference is not that drastic, so not 100 times larger or 100 times smaller. So there is more or less given depletion width for your system at equilibrium. For example, in this case, 120, and by applying forward bias or reverse bias, the width can be a little bit modulated, become a little bit narrower, or become more little bit wider. But anyway, the order is not changed that much. So I think that can be an explanation about our homework problem P1, P2, and P3. Okay, so do you have any question about these homework problems? Okay, please. Yeah, sure.
그 저번에 그 리버스 바이어스를 걸면 그 전류가 아메리카 상태가 된다고 하셨는데 저 경우에는 전류가 그 흐르는 걸로 나오는데 그 사이에 경계가
So he's now asking that now here P3 is related with our reverse biased case. So when compared with this equilibrium case P1, of course the electric field distribution is distorted. So we have a different electric field distribution compared with this equilibrium case. So his question is, okay, since the electric field is little bit different, so we have current conduction, but I told you that in this case we can have really huge current conduction, but in the reverse bias case, of course, we in principle we have a non-zero current conduction, but its value is really negligible. That was my previous explanation, and he is talking about how can you justify this negligible amount of current for this junction system. So I think that that is the point we have to understand. So let me just repeat once again my explanation done in our previous lecture. Yes, here we have an N plus region, and here we have a so-called depletion region, and here we have a p-type region. Yes. So here electrons are majority carriers, and you know there is nothing, no electron, no meaningful electron, and no meaningful host. And here we have really extremely small number of electrons, like 10 to the 3 per cubic centimeter. So you know it. And at equilibrium, there is perfect balancing between so-called diffusion component and drift component. So when you just measure the current component in this junction region, then we will find the exactly zero component. And now by applying certain forward bias or reverse bias, then relative magnitude or relative electric field between this 2 points, so depletion reason is changed. However, when we apply forward bias, then it is a weaker electric field. And if we consider reverse bias voltage, although the magnitude is the same, like minus 0.1 volt, but in this case, stronger electric field. Yes, so if electric field is a little bit get weaker, then our diffusion current cannot be compensated by this drift component. However, if we have a really even stronger electric field, then yes, previously there was nothing, and now still nothing. So let me just think about this one. Yes. I think that my explanation is not very intuitive, so instead of that, let's just think about this one. Let's say there is certain wall, and there are many particles. So they try to jump, and eventually try to overcome this barrier. Okay, there are tons of particles here. However, only very, very lucky guy can overcome this high barrier. Then now it can move into this part. This is really lucky. This is really a lucky case. Then let me just consider two different cases. So intentionally, I just raised the wall. The bar gets even higher. Then what will happen? Previously, there was a really small number of particles which can overcome this barrier. And if I just increase it further, then what will happen? We will have really small number, even smaller number of particles can overcome this barrier. Then if we just measure the number of particles which overcome this barrier, then we will say that okay, it was small, so small, and now we will say that it is even small. So previously the current was small from the electric diffusion, and now we can say that this is even smaller. So no real conduction in the reverse bias condition because the barrier gets even higher. So then think about the opposite case. We slightly reduce the barrier. Then what will happen? In this case, yes, since the bar is a little bit lower and much more particles can overcome this barrier, so we will have more particles are overcoming this barrier. So you can see that this is the equilibrium case, and when you go to the reverse bias condition, then yes, it doesn't matter. It doesn't make any meaningful increase of particle number. However, if we go to the forward bias or the reduced barrier, then we can have a lot more electrons. In this case, electrons, but electron more hole can overcome that barrier. So then natural question is, what is physical meaning of a barrier? What is the analogy of this barrier? That is actually the interpretation of a depletion region. So we have the region where we have no electrons and no holes. So that region is not very good for both of our electrons and holes, and that can be regarded as a certain potential barrier. So here we have electrons, and here we have almost no electrons, and diffusion can be regarded as, or the current conduction in this case can be considered as the movement of quite lucky electrons. Some lucky electrons. So there are so many electrons and they are always hitting this barrier. However, since this barrier is so high, so difficult to overcome, so most of them fail. However, for some of them, they can move or they can overcome this barrier, and their number, the number of lucky electrons or lucky holes, will be counted as current conduction. So I'm not quite sure that can be a sufficient explanation to your question, but if you have any further question, then please let me know. And of course, other students are also welcome to give me a question, additional question, or unrelated one. Anyone is welcome to discuss. Okay, then. Okay, your question was really related with the essential message I wanted to deliver in the previous lecture. So, simply speaking, I wanted to say in this way. All of our discussion up to now was focused on the physical origin of non-linearity. Why our p-n junction behaves differently when we apply forward bias and reverse bias. The answer, short answer, in my opinion, is internally, even when we apply just 0 volt difference in our two terminals, internally it has its own structure, which prevents the diffusion of electron and diffusion of hole. So, although at equilibrium or 0 voltage difference case, they look quite peaceful. There is nothing, no current conduction at all. However, internally, there are two competing mechanisms like drift and diffusion. So their balance is quite delicate, and if we just make a slight imbalance of this delicate balance, then our diffusion current will dominate this situation that is corresponding to forward bias. However, if we suppress the diffusion current by increasing our electric field even further, then nothing will happen. So because no meaningful or countable amount of electron conduction can be observed in this case. So simply speaking, if I summarize this one, all discussion up to now, then we can draw one simple graph. So, of course, we can consider two different terminals of our p-n junction. So, you know it's a physical reality. So, that can be regarded as n plus region and p region. And also, we can consider certain yes, we can consider certain metals on it. Here we have a certain metal, and two metals have their own name, and the one is connected to the n plus region. So n-type region is, oh, sorry, I'm not quite familiar with this one. That is called as cathode, and the one is connected to the p-type region is anode. So this is one way to visualize our system called p-n junction. But we can make another level, like another level of abstraction. Instead of considering all the details of this doping density inside our system, instead of that, we wanted to make a simplified view. So symbolic view for this system. So we just introduce this type of symbol here. Then let me just make a one-to-one correspondence between our how can I say this two-dimensional cross section. So, and this is symbols used in our circuit schematic diagram. So in this case, I can say that this O node is corresponding to this node. If you apply certain voltage, then it is physically, it is make a contact, physical contact between this metal line and another voltage source. So if you just move the tip of your, how can I say, your certain machine or instrument to apply the bias voltage, then physically it just looks like, instead of that, I just draw more realistic way. So it is like this. Here you have a certain metal tip. Yes, it is very narrow and long, and it is just placed over your metal line, and you just put it there. So in order to make a certain sure connection between them, you just push it slightly. So you know this is around 100 nanometer thick, so it does not damage the angle. So then you have a real good connection between your external wall connected to your voltage source and your anode. That is written as this form when we draw the circuit schematic. So in circuit schematic, when you just draw the diode symbol and apply certain voltage, then physically what you do is, in the laboratory, you just place the metal tip connected to same voltage source to your anode metal. Then that part is connected to this part, and internally you have PN junction. Of course, this is PN junction, and of course, what I want to say once again is, in order to make once again good connection, of course we have to have here P-type reason. However, this is P-type reason and sorry, P plus and P, but they are homojunction, so they have the same polarity, so nothing happens. So important point we have to keep in mind is only this one. Yes. So internally, when we draw in that way, this symbol is actually corresponding to the junction in here. And finally, of course, we have another, another terminal. And if we wanted to once again apply certain voltage, then we have to place our second metal tip, and that is connected to our another voltage source. So then that will correspond to our another voltage source. That is, so it is in your mind. So when you design something using, for example, computer program, then you say so. However, in order to make it realized in the physical world, and somebody should prepare the silicon substrate and implant certain dopant ions into your system and make some metal conduction, metal contacts, and place metal tips to your on those metal contacts. Then apply the voltages. Then that you will have the PN junction really operating. Okay? So then, if you observe all over the background, then I can say here we have once again so-called cathode fluid, and here we have anode. Then how about the IV characteristics of this device called PN junction? So let me just write down in this way. So voltage, the voltage can be assigned like anode voltage minus cathode voltage. So cathode is the reference one, and we will just think about the anode voltage, the difference between anode voltage and cathode voltage. And once again, if this quantity becomes positive value, then what is it? Is it forward or reverse? So, do you have any idea? So if we apply higher voltage to anode, then that is called as forward bias condition. So if we apply relatively low voltage to our anode, then we'll call that reverse bias condition. So you know it. So if we consider this case, then what we can see from now on is, if we apply forward bias, then at least we can understand is current. There will be current conduction. And if we go to this reverse bias reason, then what you can expect is, of course, the current itself is not exactly zero. So, then do we have exactly zero current in this system? Yes, we have it. So if we consider this origin, when you apply real zero bias voltage to your system, your device, then you will have real zero current conduction. That is true. But anyway, although that is not exactly zero, but we can expect that if we apply reverse bias current, reverse bias voltage, then we will have a very small amount of current in this case. So in order to give you certain feeling about this is not zero, I intentionally make a gap between our horizontal line and this red curve. However, in principle, it is not observable in this linear scale. So, usually this amount of course, depending on the area, but the size of this current, small current, is just 2 orders of femtoampere, or even more around that one. So femtoampere means femto. Femto is like 10 to the minus 15. That is the number for our prefix femto. So when you say that 1 femtoampere is corresponding to just 10 to the minus 15 ampere. So that is not that rare for our situation. So usually when we consider PN junction is extremely small, and yes, so the current itself can be really small. However, when we draw, then what will be the scale for our current? Here we have a current, and the maximum value usually we use for drawing this axis is around just 2 milliamp or micron. So compared with this milliampere scale drawing or microampere scale drawing, if you draw 1 femtoampere, 10 femtoampere, even for example 1,000 femtoampere or pico, 10,000 pico, that doesn't make any difference in your graph. So actually, you cannot recognize this small number in your, when you just open your textbook and read the drawings inside it. You can frequently find those types of graphs. However, please keep in mind that it is only exaggerated to enhance your understanding on the subject, not to say this is really zero. So we have a really small current, so its value or its magnitude is usually called as IS. So why it is called as IS? I don't know. Also, I wanted to say that this PN junction is really an important component of our industry, but it is PN junction itself is not how can I say an independent device in many cases. In many cases, a PN junction is used as a component or building block to build certain transistor. Transistor is made of several junctions, PN junctions. However, it is quite rare to just to use only PN junction to build your system. So I think that there is a certain historical reason, but I don't care about that. Usually, the signal or the symbol like I sub S later on, you will recognize it as later source current. So that is more frequently used name for this IS. However, please don't be confused with this different context. And here we have usually this one is current. So anyway, we have really, I mean that it is really small number, and there is a slight difference. Of course, without any exaggeration, we cannot recognize the difference between horizontal line, zero current, and IS. And please note that I did not draw in that way. My drawing is not in this way. Oh, what is it? Since we have applied negative bias, then current should be also negative. That sounds great. So if we draw, for example, if we draw the IV characteristics of, how can I say, a resistor, how does it look like? If we just draw the IV characteristics of a resistor, then you will find that it looks like this. It just to occupy just two, how can I say, so two quarters. So this first quarter and third quarter. What does it mean? Occupying these 2 points. So where I is positive and B is positive, and also I is negative when B is negative. So these two properties are corresponding to the sign of I and B are the same. This is quite natural. And if you consider this part, for example, here, how does it look like? In this case, we have different signs. Voltage is negative and current is positive. Also, voltage is positive and current is negative. So I can say this one. You may heard about, if you have attended the course circuit theory, then you have heard about the power consumption by certain circuit element. So do you remember? So the power dissipated by certain circuit element is given by just the product between what? Product between your I and V. This is dissipated power. So let's say you have the same, this is the end of our note. But anyway, if this is positive and if this is a positive, then what will happen to you? If I and B share the same sign, then we can immediately say that, okay, the power dissipated by this element becomes positive. And if we have negative current and negative voltage, even in this case, so we will have a positive power dissipation. So if our IV characteristics of a certain circuit elements lays on the first quarter and third quarter, then it means that your power dissipation will be positive. It means that your device just to consume the power and it just to use the electric power and convert it to in a different way. So this is just a consumer of power. However, if we are considering a system or an element called electrical battery, then you can find that their IV characteristics later on is second and fourth quarters. So think about that case. In the case, I and B does not share the sign. So when we make the product between I and B, then what will happen? Obviously, that will give us just a negative sign for dissipation power, dissipated power. So what is the meaning of a negatively dissipated power? It means that that system just to provide the electric energy into the system. That's the meaning. So then what is the source of that electrical energy? Of course, from, for example, from the chemical bonding energy, it just converted it to electrical energy. So since we are working currently with the compound called PN junction, PN junction is actually the one which just consume the energy. So the energy, electrical energy is consumed by this one. So we will have just first quarter and third quarter in our graph. So let me just conclude my short note here. So this one is really weird if we have such kind of graphs for our normal electrical component except for battery. It means that something is wrong. We have to have graphs occupying just the first and third quarters in our IV characteristics. Okay, so now I think that I have covered one part related with this reverse bias case. Then let's go to how can I say? Let's go to the forward bias case. Forward bias case, we have not talked about the curve much. So maybe just to think about this one. So simply speaking, I can write down in this way. I is very close to minus IS when we have our applied voltage which is a negative number. Okay? Then natural question is, then what will be the terminal current when we apply positive voltage? So that's the reason why up to now I have not drawn the curve here. We know that it will be positive. However, the form, how does it look like? It's like this. No, this one. Or what happens to this guy? So I just disclose the answer. The answer is quite simple, and if we just write down, then it is given by just approximately IS exponential B over BT. That is approximate form of our IV characteristics in this forward biased diode. So then maybe you feel, oh, that's so simple. I expected very complicated functional form, but I'm just saying that it follows exponential dependence. So if you increase your voltage, then what happens? If you increase your voltage, then argument of your exponential function is increased too. So you will have a larger number from this exponential function, so your current will be increased. So that is quite simple. So let me just draw it. And please draw the how can you say the graph for please draw something like y equal to exponential x. How does it look like? So can you expect same thing like this? So I think that you all passed your high school courses. So during that time you have drawn exponential function so many times, and exponential function doesn't look like this. This is just the exaggerated form, and if I draw more realistic way, then it just looks like this. So y and x, and if we draw exponential function in a certain scale, and then it's not like this. It is. Oh, let's see. Well. Okay. So it just to depending on your maximum value. So please note that. Let me just do it together with you. So I just, when I draw this exponential x, I just say, okay, I will use 1 as the maximum of my graph. Then what will happen? If we have such kind of thing, then you will have just this way. But instead of this 1, I just say that 10 to the 12. 10 to the 12 will be the maximum of my y equal to e to the x graph. Then what will happen? In this case, your curve doesn't look like this. If we have 1, 10, something, there will be certain range. Your exponential function has its own value, but much smaller than our maximum value for our visualization. So you will have something like this shown here. Up to certain value, your y equal to exponential x will have non-zero value, but it is much smaller than your maximum value for visualization. So what I want to say is, always think about the range of your graph. So this is one thing. It is very easy to be overlooked. So usually when we draw IV characteristics, sometimes I can say that the current is negligible, or there is almost no current at all. I can say in a plain English something like that. However, please note that if we just have a look at the graphs in a really magnified view, for example, if we are talking about the femtoampere scale graphs, then that becomes a really meaningful quantity. So whether that is important or not is determined by the scale. If you are care about femtoampere current, then that will be real important. However, if you are talking about just the ampere scale or milliampere scale curve, then this curve, this guy, can be safely regarded as just nothing. So please keep in mind that when we consider this forward bias current, then what is your ranging for current conduction? That will be certainly about milliampere or microampere scale for microelectronics, and that requires certain, how can you say, certain voltage to make your system be sufficiently turned on. Only after certain voltage, then your exponential function will just fly like this. So are you all with me? So I'm just saying that please this is not the homework program, but please come back to your dormitory room or library and please try to exponential function. Same exponential function, however, in a linear scale, linear y-axis scale, and changing the maximum of your graph, then you will immediately find out what I'm talking now. So if we are talking about milliampere scale, then your curve will look like this. But if we go to, for example, just 1,000 times magnified view, then your curve doesn't look like this. And your curve will have much shorter range required for turning on your device. After that, your curve will look like this. Okay? So, then you can think about this one. So I think that this is now it's a time to talk about very important concept about this system. Let's assume that your IV characteristics of a PN junction really follow certain number. Exponential variability. Please assume this dependence. And I wanted to ask you, please assume certain IS. You know it. For example, you can assume 10 to the minus 15 or 10 to the minus 12, whatever, you can assume certain number. And please assume this number. So here we have V sub T, and it has its own name. Its name is summer voltage. So why do we have summer voltage appearing here? It is related with semiconductor physics. So if you are really interested, then I strongly recommend you to attend our more advanced course, like semiconductor materials and devices. But I wanted to say this summer voltage is related with the temperature of your system, and at 300 Kelvin. So 300 Kelvin is typically called room temperature, and its value is about 20.85 millivolts. So maybe it is good to remember this number. Anyway, this is 25 millivolt is just 0.025 volt. So it's not that large voltage. So here, this is a relatively small scale. But anyway, now let's think about this one. Under this assumption, please assume that at V equal to V naught, we have no idea about V naught, but you have current which is given by 1 milliamp. Please assume this one. Then my question is, then at which bias voltage? So can you understand? So let me just explain it further. So I think that this is a really important concept during our semester. Say that we previously, for a certain voltage assumed to be V naught, we have no idea about what is it. But anyway, when you apply V naught to your device, you have 1 microampere. Yes, let's assume. Then, when you try to increase the current by a factor of 1,000 or 3 orders of magnitude higher current, how much additional voltage is required for your device? That is my question. Are you with me? So, for example, I'm now saying if we just stick to certain number, example number, then I'm asking So, for example, if we apply 0.5 volt from our PN junction, we can get the terminal current to 1 microampere. Then, in order to get 1 milliampere, which is 3 orders of magnitude higher than 1 microampere, how much the voltage should be applied to this device? Maybe you feel that it is very difficult, but let's do it together. Okay? So let me write down here. Following our assumption. So 1 microampere is appearing Is exponential V naught plus Vt. It is assumed. Then our assertion is, okay, we wanted to have 1 milliampere. And what is the applied bias voltage? Then we will follow the same one, Vt, and the voltage we don't know. So are you with me? So this is the assumption in our problem, and the second part is the one we wanted to calculate. This question mark voltage is our answer. We wanted to the voltage, how much we have to apply to get 1 milliampere. But we can, instead of this question mark, this looks ugly. Instead of that, let's say this unknown voltage is given by V naught plus delta. We have no idea what is this delta, but anyway, let's assume we have applied additional voltage to increase our terminal current. Then, by dividing these two equations, left hand side wise and right hand side wise, what you will get is, okay, you will have 1000. When you divide 1 milliampere by 1 microampere, you have 10 to the 3. And when you divide this number by this number, then what will happen? The leading coefficient like Is or exponential V naught, they are all cancelled out because we have made a division operation, and remaining thing is just exponential for delta and Vt. So if you have any question, then please interrupt me. Then you can easily understand from this consideration. Now, you have 10 to the 3 is exponential delta Vt. And if we take just to, for example, natural logarithm for both of them, then we will have 3 times natural logarithm of our 10, and we will have delta divided by Vt. So then finally our answer will be the additional applied voltage to increase our current by factor of 1000 will be given by just 3 times Vt log 10. So, do you have any question about my simple exercise? The assumption is, in the forward bias operation, our diode current or junction current follows this exponential form. And by assuming this form, we just build 2 cases. One case is 1 microampere current conduction, and another case is 1 microampere current conduction. This is the expression. This is 1 microampere, and this is 1 milliampere current conduction. And when we just compare them by making the division of left hand side and right hand side, then we will find that the required the required voltage for our junction to increase the current by factor of 10 to the 3 is given by 3 times Vt log 10. Then I wanted to change my mind and wanted to ask you another question. Instead of this 1 microampere, instead of this 1 microampere and 1 milliampere, 10 to the 3 times difference. If I ask you 1 microampere and 10 microampere case, just one orders of magnitude increase of our current conduction, then how much we have to apply additionally to our current? Then what is the value of required delta? You can easily understand this number 3 is corresponding to 10 to the 3, the power of 10. So you can easily understand, in this case you have to apply Vt log 10. Then let me just once again, let me change my question once again. If we have 100 times increase of current conduction, if we wanted to increase it by factor of 10 to the 2, then of course we have to introduce 2 times Vt log 10. Oh, yes, that's all. So if we wanted to introduce 1 million times difference, then how much the voltage difference is required for the current, our terminal voltage? Then 6 times this Vt log 10. So you really immediately realize that this number Vt times natural logarithmic of 10 really works as the scale for increasing your terminal current by factor of 10. So if you apply this amount of voltage additionally, then your current will be just 10 times larger. So then natural question is, what is the exact numeric number for this Vt log 10? Vt log 10. At room temperature means that at 300 Kelvin, this numeric value of delta is easy to remember. So it is just 60 millivolt. So it is time to be surprised. So 60 millivolt means that 0.06 volt. It is even much smaller than 0.1 volt. So in your diode, when you just slightly increase your voltage by amount of just 60 millivolt or 0.06 volt, then you can easily increase your current by a factor of 10. Then think about this amazing number like 10 to the 6. Oh, your current is now changing orders of 6 orders of magnitude. For example, 1 picoampere, from 1 picoampere 10 to the minus 12 ampere. Now your current can be increased 10 to the minus 6 ampere, 1 microampere. You have a huge difference between these two cases, and in order to achieve that difference, how much voltage difference is required for your system? You just apply 0.36 volt. Much smaller than even 0.4 volt. Within just 0.4 volt, you can change your current value more than 6 orders of magnitude. So I wanted to say that this exponential function is really sensitive to your forward bias voltage. So if we where is my previous video? So I have deleted. So let me just draw it once again here. So so as I told you before, our IB characteristics is really have some dependencies on the maximum value. For example, if we just fix our maximum value to 1 microampere, then we will have this form for our graphs. However, if we just extend our maximum value not to 1 microampere but to 1 milliampere, obviously we will have slightly shifted curve. Yes. However, that shift, how large is it? What is the difference now? Now you can understand. Since the scale for terminal current is changed by factor of 10 to 3, so you will have just 0.18 volt difference for your changes. So now, so first of all, I wanted to ask you, all of you are with me, about this quite interesting behavior. So this quite interesting behavior of our PN junction comes from the assumed expression like this. This one is such kind of interesting behavior. If our terminal current follows the exponential dependence on the applied bias voltage, then it will just look like this, and at room temperature, actually, regardless the how can I say, the maximum of our Y scale, the current scale, anyhow we will have very narrowly distributed IB characteristics. So for your PN junction. So therefore, yes, what is the exact value of this the voltage where the our IB characteristics now just to shoot up? So we have no idea. It really depends on your implementation. If you have a different PN junction, then the voltage will be slightly different. However, what we can say certainly is, although exact form is different between this implementation or that implementation, but anyhow the difference or distribution of this curve will be very narrow. So usually typical number we assume in this course is about, yes, for example 0.7 volt or 0.8 volt. So of course you can ask me, why do we say 0.7 or 0.8? 0.6, is it acceptable? 0.5, is it acceptable? Well, then the decision should be made based upon our situation. So we have no predetermined or rigorous definition about this value, but roughly say, okay, if we apply certain voltage around 0.7 or around 0.8, then maybe this PN junction now ready to conduct our current. Now it is certain that if you apply, for example, just 0.1 volt, then what will happen? If you apply just 0.1 volt, yes, since it is a forward bias voltage, your PN junction now conducts certain current. But from my point of view, here mine is that the application side, the current conducted by that small amount of forward bias is not enough to be counted as reasonable current conduction. So we just neglect that number. Oh, the device is not yet turned on, and we have to apply further voltage, much more voltages to really turn on. And as I told you before, 0.7, 0.8. This is there is no strict value or definition about this number, but we use to say that 0.1, your device is turned on, not, then certainly we can say that, oh no, certainly this device is not sufficiently turned on. For example, 0.3, no, maybe not. 0.5, also maybe not. And 0.7, and then depending on your scale, you can say that, oh, maybe we have to be careful about estimating its current conduction or not. Okay? So, do you have any question about the behavior of this PN junction? So, today's lecture now has been devoted to the description about IV characteristics of our system called PN junction, and we have considered the reverse bias and forward bias. And interestingly enough, we have a completely different behavior when we have really negative or reverse bias operation. Then we have almost vanishing current, although not exactly zero, but it is several orders of magnitude smaller than our usual application window. Okay. And if we go to forward bias case, then instead of this negligible current, we have a really powerful current conduction. But it's not like just on and off. Although exponential function is really rapidly increasing one, however, in order to meet our goal, like a maximum, like a microampere or milliampere, it needs certain voltage, and the voltage required to this device turned on is related with this scale, very important scale called Vt times log 10. And this is the numeric value at room temperature is 60 millivolt. So please remember this number. I think that this number is really important for microelectronics. At room temperature, you have to apply 0.06 volt or 60 millivolt to increase your current by factor of 10. So think about this one. You wanted to make a switch. When you make a switch, your requirement is your on current and off current should be at least 6 orders of magnitude difference. So your current in, so let me get, when you try to turn on your device, your device should conduct 1 milliampere, more than 1 milliampere. This 1 milliampere is minimum requirement. And when you turn off your PN junction, then your current should be lower than 1 picoampere. Let's assume that. Micro is 10 to the minus 6 and pico is 10 to the minus 12. So we just stating that at least we have to have 10 to the 6 times difference for on current and off current. Let's assume this case, this situation. And if we try to achieve this kind of switch by using microelectronics, then at least we need a voltage room. The minimum voltage room required for achieving this kind of switch is simply given by 0.36 volt. So are you with me? Because in order to increase one order, we need 60 millivolt. And what we have to do is increase the current 6 orders of magnitude. So 6 times 60 millivolt is required. So that is the number. It means that nowadays we are all of us having a cell phone, and in order to increase our battery life, then we are willing to decrease the operation voltage. However, if our requirement is really 10 to the 6, then our operation voltage cannot be reduced below 0.36 volt. Of course, if we require more severe values, like 10 to the 8, then what happens? Then there will be just 48, 0.48. So it is, this number is really the killing factors for our future electronics. With this conventional electronics technique, it is very difficult to reduce the operational voltage. So that's the reason why nowadays, so engineers are working, or physicists together, they are working on new mechanism to operate our electronics. But anyway, if we just follow the conventional way, please remember that at 300 Kelvin, in order to increase our current by factor of 10, at least the minimum requirement is, 60 millivolt. Of course, we have many fancy ideas to overcome that limitation, but it is much beyond the scope of this course, and I'm not talk about it. And we have just only 1 minute, and my last minute will be devoted to the unified form of our hybrid characteristics. Maybe you are not very happy with this separation. So reverse minus IS and 4 exponential something. So you don't like it. So let me just give you the unified form as the final equation of our that is the unified form of our equation. You can easily understand if we assume this kind of dependence that is reduced to just minus s when you apply negative v, and if we go to positive v, then we will recover the expression for forward bias voltage. Okay, and the best thing is when you apply just 0, then what will happen? This exponential term and minus 1 will be cancelled out. Oh, so therefore we have a perfect zero conduction at zero bias voltage. Okay, good. And in the next lecture, we will move to how can you utilize, or how can you utilize and how can you analyze this a system with PN junction. Okay? So since time is up, I will just wrap up here. And if you have any question, then please send me your mail. Okay, thank you. Bye.